And today we are talking about combustion and cracking. I'm going to do this as a two-part lesson. So first we're going to look at cracking and then we're going to look at combustion. So in cracking, we're going to describe the process, explain why it's needed, state how we can use the products and how we will test for the presence of the products, and look a little bit at balancing equations as well. First thing I would like you to do is pause the video and answer these three questions. Give me 5 products from crude oil. Draw the chemical structure of decane, and I mean the displayed formula, and why is this molecule not useful? Pause the video now. So, 5 products from crude oil. You could have had petroleum gas, petrol, kerosene, diesel oil, naphtha, and bitumen, or residue, you might have called it, and that's fine. Chemical structure of decane. Decane, that means 10. So we've got 10 carbons. 10 carbon chain. And then our hydrogens attached to each of those carbons, like so. A little bit repetitive, this one. Last one. And that is your displayed formula of decane. Why is this molecule not useful? It is too big. So we mainly want to get fuel out of our crude oil. Decane is quite a big fuel. It'll be quite thick. Might be a thick liquid or a solid. The bigger the chains are, the thicker your liquid or the more solid they become, and then the harder they get to burn. Okay, decane, although it's not the biggest, is fairly big, so it doesn't burn very easily. So from our decane molecule, split that into 2 smaller molecules and have to think about naming the products that you have made. So you can pause the video now if you want to do that. I'm going to split my decane molecule into four carbons on one side, 6 carbons on the other side. Now I will draw my hydrogens on each side. Now this side, I'm just going to keep it like this. But on this side, we're going to have to do something a little bit different. Okay, mainly because we've got a missing bond, and that missing bond is going to go here. Okay, so rather than having the bond between these two, I've got a missing bond. I'm going to put it here instead. This means that my hydrogens form a little differently, because each carbon can make 4 bonds. So this carbon makes 1, 2, 3, 4. This carbon needs to make 4 bonds, 1, 2, 3, 4. And this carbon needs to make 4 bonds, 1, 2, 3, 4. Okay, so we've got 2 slightly different chemicals being produced. In terms of naming them, we've got 4 carbons here. So this is butane. This one, we've got 6 carbons and a double bond. So this is hexene. Okay, notice that rather than an ane, an alkane, we've now got ene, an alkene. Okay. We could have done that the other way round. So instead of having our double bond here, we could have had our double bond here. That would mean this carbon would only have 2 hydrogens attached. This carbon would only have 1 hydrogen attached. So we've still got 4 bonds. This would now be butene. And here, this would stay as a single bond. Each one of these would have a hydrogen attached, and we've made hexane. But in either case, however you split this molecule, you're always going to make 1 alkane and at least 1 alkene. Okay? Now you may have done it differently, that's fine. You may have had 8 carbons and 2 carbons, or 5 and 5, or 7 and 3, that's fine. Okay? The key thing there is, can you name what you have made? So cracking is a process where we break a large hydrocarbon down into two smaller, more useful products, alkanes and alkenes. So let's name some of those more common alkanes and alkenes. Hopefully you are familiar with methane, ethane, propane and butane. Okay, and that you can remember that M is 1, E is 2, P is 3, B is 4, pentane is 5, then hexane 6, heptane 7, oct is 8, non is 9, dec is 10, and so on. Okay, so methane. CH4. Ethane, 2 carbons, and so each carbon has a hydrogen attached. C2H6. Propane, 3 carbons. Butane, 4 carbons. Pentane, 5 carbons. Each carbon making 4 bonds. You can fill those ones in. Okay, so that's your alkanes, most common alkanes. Let's have a look at the alkenes. I'm going to work my way backwards. So an alkene has got a double bond between 2 of the carbons. So just to keep things easy, I'll always do that at the front. Pentane still needs to have 5 carbons. Four bonds for each. So each one of these will be hydrogens attached. So we've got C5 and then 2, 3, 4, 5, 6, 7, 8, 9, 10. H10 as our formula. Butene, again I just put the double bond in the first bit. 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Propene, double bond there, and 3 carbons. Ethene, double bond there, 2 carbons. 1, 2, 3, 4, 5, 6. This is going to be C2H4. Each one of these only have a 2. Methane can't exist because I can't have a double bond if I've got no other carbon to bond to. So methane does not exist. Okay. So you should have covered that in yesterday's lesson, but just there as a little reminder for you. So pause at any time if you need to go over that. Don't forget you can use a general formula for both of these. General formula for this one is going to be N to N plus 2. Okay, so for example C3, 3 is N, 2N plus 2 is 8. This side is just CnH2n. So let's get back to our main topic, which is cracking. So cracking can be done in industry or in the laboratory. So this is the setup we use, and we are going to watch a quick video now, and I will show you how we would do this in the lab. So we are going to show you how to perform cracking in the lab. So we are cracking paraffin fuel, which is quite a large hydrocarbon, and we're going to crack it into smaller hydrocarbons, alkanes and alkenes. So first thing that I need is some mineral wool. So I'm just going to push that down to the bottom of my boiling tube, like so. And then I'm going to soak that mineral wool in our paraffin. So I need quite a bit in order to get a good amount of gas produced. You can see that it's quite viscous. That's because it's a large hydrocarbon chain, which means it will take just a little while to soak right down into my mineral wool. A little bit more so that it is properly soaked right down to the bottom. Okay, so I'm happy that that mineral wool is nicely soaked. So I'm just going to soak up any excess, because we do not want it to tip down the boiling tube. That should be fine, like so. I'm going to move my paraffin out of the way. Next, I need a catalyst. Although we're going to heat this to quite high temperature, it is the catalyst that is actually going to help our cracking to occur. And we just use these bits of broken pot, as you can see here. Other people can have used pumice stone, bits of pumice stone, little bits of terracotta pot would also work. I'm just going to put this in. Obviously, the more you use, the bigger the surface area, and the surface area will also help to improve our cracking time. Should help it happen a lot more quickly. Try and get some of these really small bits, which have a larger surface area to volume ratio, and you kind of want them in the middle of your boiling tube, like so. I'm then going to place very carefully onto my clamp stand. And you'll notice that I have clamped it right near the end of the mouth of the boiling tube. And I'm going to place a bung inside. And this bung is connected to a delivery tube. And that delivery tube is going to go into this bowl of water where we've already set up 6 or 7 test tubes full of water and bungs. They are going to collect our gas, which we're then going to just store here so we can test to see what gases we have got. So Mr. Aero is going to help me do that, because this is a 2-person job. So first thing I'm going to do is start heating on a roaring blue flame. And you'll notice that I'm heating the porcelain chips first, so that I can get it all really, really nice and hot. So you want to get that heated for about 10 seconds. I'm using the area of the Bunsen burner just above the blue cone, because that will ensure that's the hottest part. So heated my porcelain chips. So now I can just start heating my paraffin. A couple of seconds on my paraffin and then back to my porcelain chips. Main reason for doing that is that you want to keep everything really, really hot. The longer you heat the paraffin, you'll actually cool the system down, and that will create suck back. So that is when the water will be sucked back along the delivery tube and into my boiling tube, and that could cause it to crack, which would be very dangerous. If I did see water coming back, the temptation would be to stop heating, which of course is the worst thing you could do. You actually have to heat it more strongly whilst removing the delivery tube from the water, and then keep heating to try and force that water back out. Still making sure it's getting nice and hot. See, we've collected one lovely test tube of our gas. We need to collect about 6 test tubes of gas in order to make sure we've got enough of our products to test. The first couple of test tubes are mainly air, just from the system, so we want to remove that. And so it will be our last 4 or 5 test tubes that are going to be important. Keep it nice and hot. I should be collecting my gas now quite quickly, which is good. I'm actually using a special boiling tube, which isn't made out of glass. It's made out of a certain type of glass, which can withstand higher temperatures. You'll find if you try to do this with a test tube, it would probably melt, so wouldn't be very good.
No advice.
So remember, the reason that we're doing this is because our bigger, longer hydrocarbon chains are not always that useful. They tend to be solids or very thick liquids, which don't burn very easily and don't burn very cleanly. whereas our smaller products make much better fuels if they're alkanes. And our alkenes can be used to make polymers, things like plastics. So we're just going to collect one more test tube's worth. It shouldn't take too long, it's bubbling away nicely. Keeping my porcelain chips nice and hot. Just keeping an eye on my tube here in case any liquid starts moving up. So far so good.
Almost done. We've made it.
And there we go, 6 test tubes full of our products. So now I'm going to remove my delivery tube from the water. Just going to keep heating for a little bit longer, just to ensure that there is no water left in the delivery tube. Keeping it all nice and hot. And then when I'm satisfied, I can stop heating, turn off my Bunsen burner. I'm going to step away just in case. So you saw how we carry out cracking in the lab. It's quite a fiddly process, but it requires a lot of heat. It requires our mineral wool soaked in our hydrocarbon, so our paraffin oil, our porcelain chips to act as a catalyst, and then our delivery tube to collect our gases, and then our water to displace the gas and collect it in our test tubes. Cracking in this way is an example of thermal decomposition. Okay, so it's thermal decomposition because we have broken down that hydrocarbon using heat. So we've heated it up and it's broken down into our 2 smaller fractions. Porcelain chips, as I said, is a catalyst. Okay, you must know this key term, thermal decomposition, breaking down using heat. This is how we would do it in the lab. You can also do it in industry. So here we have large hydrocarbons being broken down using very, very high temperatures, much higher than we could get in the lab, in school, and a very hot catalyst. Okay, so this is also known as catalytic cracking. Once we have done that and we've got all of our different smaller molecules, we can then use distillation again to separate those smaller molecules. So our big molecules are put in here. A lot of heat is added and that vaporizes them. Lots of heat and pressure. They go through our catalytic cracker, getting smaller and smaller, and then we can separate them in our distillation tower to get our smaller molecules. So, as an example, we have our decane again. If we add lots of heat and pressure, I can make this molecule, which has got 1, 2, 3, 4, 5, 6, 7, 8 carbons, which means my other molecule has to have 2. And because this is an alkane, the other one has to be an alkene. And here we go. We have our ethene. This one has 8, so it must be octane, and our ethene. If we were to write out the formulas, C10H22, which is this one, goes to C8H18 plus C2H4. Okay, so that is an example of writing the formula for catalytic cracking. So cracking is really useful because we can take our large, not very useful products and turn them into smaller, more useful ones. So our smaller alkanes that we make can be used as a fuel, and we're going to look a bit more at that when we do combustion in part 2. Our alkenes are used to make polymers. So anyone that does triple, we can use alkenes to make the polymers that we can then make into different types of plastics and other useful chemicals. Now there's a special test that we can do to test for alkenes, which I'm going to show you. We add something called bromine water. So bromine is this kind of red colour. And when you add that to an alkene, that red colour disappears. Okay, we're going to watch a video now where I can show you using our laboratory cracked fuels, which ones are alkenes, and then have a go at why the bromine turns colourless, why it stops being red. So now I have collected my test tubes with my products, I can test to see what they are. Now these first two will be mainly air that was just in the system, so I'm going to actually just get rid of those two because they're not going to tell me very much. Now my next two should contain some alkanes. Okay, they're the gases that would have come off first. So I can test an alkane basically by seeing how easily it lights. So I should be able to ignite the gas if there's enough. Maybe not in that one. Let's just see if we've got any in the next one. There we go. You can just see the tiniest little flame there. It did ignite, which shows us that we did have alkanes present because it ignites very, very easily. Now my next two should contain alkenes. There's two different ways that we can test for alkenes. We can use bromine water and we can use potassium permanganate. So potassium permanganate is this lovely pink colour. If there are alkanes present, it should go colourless. There we go. So it has lost its pink colour, so that has shown us that there is presence of alkenes. And our bromine water is very similar. So bromine water is brown in colour. So I'm going to, again, put some bromine water into the tube. Got this sort of yellowy, browny colour. Give it a shake up. And you can see again, it has gone colourless. So that has shown us presence of alkenes. And I'm going to carry on with our video and show you how that actually works. So there we go. So you can see our alkenes were turning our bromine water colourless, but why does this happen? So this here is an alkane, this is ethane, and this is an alkene, this is ethene. Now if I was to mix bromine with this alkane, nothing would happen. But if I mix it with an alkene, this alkene has got things that it can do because of this double bond. Okay, this double bond can break, which means each carbon has now got an extra bond that it can make, which means it can now bond with our Br2. We've got two lots of Br, so each carbon can have one bromine each and can still also bond to our hydrogens. So I've not lost any of the hydrogens. All I've done is I've lost this double bond and allowed each carbon to bond to one bromine atom each. In this form, because the bromine is now part of another molecule to become a compound, it loses its red colour and it becomes colourless. So that is why your bromine water can turn colourless with an alkene. And then that just shows it there for you. The more double bonds there are, the faster this happens, because you can make more of that bromine as part of a molecule. So, just to summarise, catalytic cracking involves large hydrocarbons being broken down into smaller chains using heat and a catalyst. It is an example of thermal decomposition. Products are separated by fractional distillation. For example, decane through catalytic cracking can become octane and ethene. Octane we can use as a fuel, which we'll do about next, and ethene we can use to make polymers like plastic. So that brings us to part 2, which is combustion of fuels. We're going to look at the products of combustion, how we can test for those products, and we're going to look at incomplete combustion as well. First thing I would like to do, pause the video and complete this equation for the combustion reaction. Off you go. Okay, hopefully you've had a really good go at that. Whenever you have combustion, you are always burning something with oxygen. So we've got to have oxygen here. Products of combustion are always carbon dioxide and water. Now all we would need to do is to balance that out. So we would need to put a 2 here, 2H2, so we can make 4 hydrogens here, 4 hydrogens here. That means now we've got 2 oxygens plus 2 oxygens, 4 oxygens altogether. So we put a 2 here, and then we've balanced out that side as well. So we've got 4 oxygens here. So definition of combustion is the oxidation of fuel using heat, and it requires oxygen. So you have to have oxygen in there. So carbon dioxide and water were our products, and we can actually test for those products in the lab. Okay, using a setup a little bit like this. So we have our fuel that we are burning, and we're just going to put a funnel to capture our products, and then we're going to see if we can test our products to prove that we have got water and carbon dioxide. So here is our setup to show the products of combustion. I have got my fuel, which is ethanol, a funnel to collect the products which are going to go into this U-bend tube. I've got some blue cobalt chloride paper ready to go in there, lime water in here, and then it's just set up on a tap to help draw the gases through. So I'm burning ethanol. Here is the formula. Let's see what we're going to make. So ethanol is burning, and you can see already in my U-bend tube there is some condensation. So that condensation is from the water that is being produced, and my cobalt chloride paper is no longer blue but turning white. That shows the presence of water. And if we have a look further along at my lime water, we can see that it has gone cloudy. And cloudy lime water is a positive test for carbon dioxide. So using this bit of equipment, we can see that the products of burning, or the products of combustion, are water and carbon dioxide. So our cobalt chloride paper, as the water condensed, it made it go blue, which showed the presence of water. You can use a boiling tube like this, or you can use a U-bend tube within ice. This just helps it go a bit faster than using it in this method, but both are doable. Lime water in the end one, if carbon dioxide is bubbled through lime water, the lime water will go cloudy, and that is what we saw. So it proves that water and carbon dioxide are being produced. So the cobalt chloride paper went blue to prove water, the lime water went cloudy, and that proved the presence of carbon dioxide. So what I'd like you to do now is have a go at writing the word and symbol equations for the combustion of these 4 hydrocarbons. Pause the video now, write them out, and then we'll go through the answers. Off you go. Hopefully you had a really good go at that. So all of them are going to be plus oxygen goes to carbon dioxide and water. That should have been fairly easy. It's the symbol equations that may have been a bit more tricky. So let's go through each one. Methane is CH4 plus oxygen. We're making carbon dioxide and water. Now we covered this right at the beginning of this section. So in order to balance that out, we need 4 hydrogens on each side. So I'm going to put a 2 in front of my H2 to make 4 altogether. I've now got 2 oxygens, plus 2 oxygens is 4 oxygens on this side. So I need 4 oxygens on this side, so I can put a 2 there to make 4 oxygens, and I am balanced. That's probably the easiest one. Let's step it up a bit. Ethane. Ethane is C2H8. No, it's not. It's H6, sorry. Because it's 2N plus 2, so 2 times 2 is 4, plus 2 is 6. Again, I'm plusing oxygen, I'm making carbon dioxide, and I'm making water. This time I've got 6 hydrogens here, so I'm going to put a 3 there to make 6 hydrogens on this side. I've also got 2 carbons here and only 1 here, so I need to put a 2 in front of the carbon to make 2. That now means that I've got 3 oxygens there and 4 oxygens there. Okay, so I've got 7 oxygens on that side altogether, but only O2 here. Now, you can do decimals in a balanced equation. Okay, so in order to get 7 oxygens here, this would need to be 3.5. Okay, and that's perfectly okay. You are allowed to do that. You can up it all by 1 if you wanted to. So you could make it 2C2H6, 7O2, 4CO2 plus 6H2O, and then that should still work out. So 4 carbons, 4 carbons, 12 hydrogens, 12 hydrogens, and then 14 oxygens, and this would be 8 plus 6, which is 14. Okay, so that would be perfectly fine. Propane, C3, 6 and H8, plus oxygen, CO2 plus H2O. 3 carbons, so let's start by putting a 3 here. 8 hydrogens, so let's start by putting a 4 there. Count up your oxygens. 4 plus 6 is 10. Put a 5 there to make that 10. Quite nice and straightforward. And finally butane, C4H10 plus oxygen goes to carbon dioxide plus water. 4 carbons, let's put a 4 there. 10 hydrogens, so let's put a 5 there. And then that now means that I've got 13 oxygens. I'm going to have another decimal one, so I need 7.5 here. And again, you can up that all by 1 to take out the decimal and have 2 C4H10, 13 O2, 8 CO2 plus 10 H2O. And that should still all balance out, so let's double check. 8 carbons here, 8 carbons here, 20 hydrogens, 20 hydrogens, and then I've got 16 plus 10, 26 oxygens, 13 times 2 is 26, so I'm balanced. Okay, so although we're using really big numbers, we've still got it to balance out, and that's absolutely fine. So well done if you got to any of them. The next bit we're going to look at is incomplete combustion. So incomplete combustion occurs if I do not have enough oxygen. So I want you to pause the video now, click the other link that I've sent you in EduLink to watch this video here, and then answer these 4 questions. What is causing the deaths? How is it produced? Why is it called a silent killer? And how does it cause those deaths? So pause the video now and go and watch that other video. Off you go. Welcome back. So hopefully you've watched the video and have answered those questions. So what is causing the deaths? The deaths are being caused by something called carbon monoxide. Okay, mono means 1, so that would be its formula, CO. Carbon dioxide would be 2 oxygens, we've got 2. Carbon monoxide is just 1 oxygen. How is it produced? It's incomplete combustion, which is burning without oxygen or burning with not enough oxygen. It's called the silent killer because it has no taste, it has no smell, you can't see it or hear it. Okay, so there's really no way to know it's there, kind of until it's too late, or until you certainly start feeling the effects of it. How does it cause deaths? So in the body, bit of biology now, what it does is it binds to the hemoglobin in your blood. So normally your hemoglobin binds with oxygen to become oxyhemoglobin, and then your red blood cells carry that around your body to your respiring cells. But here, the carbon monoxide binds instead, and it binds permanently. And that means that no oxygen can bind. So if the oxygen is not binding into your hemoglobin in your red blood cells, you are not going to be getting oxygen around to all the respiring cells in your body. So respiration levels are going to go down and you're going to lose energy, which is why some of the symptoms start off as sort of feeling tired and feeling nauseous, because those sort of normal processes just aren't happening. In combustion, as well as carbon dioxide and water being produced, there are other impurities. So lots of fuels contain sulfurs and nitrogen, and when they burn in air, they become sulfur dioxide or nitrogen oxides. Sulfur dioxides and nitrogen oxides are forms of pollutants, and you will learn more about that when we look at pollutants, when we do about the atmosphere. And soot can also be produced. Soot is basically just a solid, lots of very tiny solid particles, and they sort of remain in the air like a dust, and that can cause its own problems, like respiratory problems. So it's another form of a pollutant, and again we will look more into that when we do about the atmosphere. That's the end of today's lesson. I hope you enjoyed it, and we'll see you soon.